Baseball great Jackie Robinson was quoted as saying, "A life isn't significant except for its impact on other lives." While the term significant is important in this quote, it doesn't mean the same thing when applied to research. This video will focus on what statistical significance is, the difference between a statistic and a parameter, and confidence intervals and confidence levels. And we'll wander a bit along the way to cover some related points. Before we cover what statistical significance means, let's talk first about what it doesn't mean. And for that, we'll turn to our trusty Oxford Dictionary, where the first two definitions of significance are general and abstract, relating to importance or meaning. We often say things like, "the most significant point is," or "he gave her a significant look." Both examples where the word significant is synonymous with importance or meaningful. But when we use the term significant in referencing research findings, the key concept is not importance. For that, we can look at the third definition offered by the Oxford Dictionary, the extent to which a result deviates from that expected to arise simply from random variation or errors in sampling. In layman's terms, it means that we are trying to find out whether a result is due to chance or sampling error. Let's say we conducted a study focusing on the Three Stooges, a comedy and vaudeville act popular in the United States during the mid-20th century. Their comedy was based in slapstick humor, lots of head slapping, eye poking, running into things. Many Americans laughed at their pain and their bumbling nature. We asked 400 people the question, "How funny do you think the Three Stooges are?" And we come up with the following statistics. 34% said very funny, 41% somewhat funny, and 25% said not at all funny. And of course, this data assumes that everyone knows who the Three Stooges are. You should be asking yourself, what is the likelihood that these results, gathered from a sample of 400 people, are an accurate representation of the overall population? Or conversely, how likely is it that these results were due to chance or sampling error? This is the core of statistical significance. If you are working with a sample rather than the entire population, there is a possibility that you can collect, simply by accident, a sample that is not representative of the population. Let's go one step further and compare these results by sex. The males in our study were more likely than females to classify the Three Stooges as very funny by more than a 2-to-1 ratio, and almost 3 times as many females than males thought the Three Stooges were not at all funny. But we have to ask ourselves, is what we are seeing reliable? How likely is this difference that we observed real or true? Or, as it relates here, is there a statistically significant difference between the answers of males and females on the assessment of the Three Stooges' humor? We'll get back to that, but let's switch topics for a moment. Another word that people often misunderstand as it relates to statistical research is the word statistic. Many people think of a statistic as any number, whether expressed as a percentage, as in 20%, a proportion, such as 0.2, a fraction, as in 1 in 5 or 1/5, or as a raw number, like 245. But that's not quite right. To really understand this, you need to know the difference between a parameter and a statistic. A parameter describes a population, the entire population, while a statistic describes a sample of the population. We use a statistic to generalize what the parameter is, or said another way, we estimate parameters based upon statistics. For example, if you want to know what the entire U.S. population thinks of the Three Stooges, and you conducted a survey of, say, 400 people nationwide, you would end up with a statistic, which you would then generalize back to the entire U.S. population. The research community considers this an important enough of a distinction that it uses different symbols, depending upon if the numbers reported represent a sample or a population. For means, as an example, the symbol you use to show that the arithmetic average you are reporting refers to a sample is X bar. You are reporting a statistic. While if your mean is derived from a population, you are reporting a parameter, you would designate that with the symbol mu. Other common examples of using different symbols to clarify the number you are reporting represents a sample or a population are standard deviation and the number of observations in the data set. Back to statistical significance. Remember that if we are working with a sample rather than the entire population, there is a possibility that our sample may not be representative of the population. In our example of the Three Stooges, how confident are we that our survey results, conducted of, say, a sample of 40 people, can be generalized to the larger U.S. population, which at this time is close to 320 million. Even though the differences may look big or important in our results, I would be reluctant to generalize these statistics from this small of a sample back to the overall population. But if we increase the sample size to 400 people, well, that increases my confidence level as well. The larger the sample, then, the more confident we can be that the sample statistics reflect population parameters. That takes us back down memory lane to the normal bell curve and standard deviation, where you'll recall that about 68% of the scores in a data set, where the data are normally distributed, would fall within one standard deviation of the mean, about 95% within 1.96 standard deviations, and about 99% within 2.58 standard deviations. Therefore, if we can assume a normal distribution of values in the sampled population, we can use parametric statistics to calculate the probability that our sample has captured the characteristics of that population. But how confident can we be? That brings us to two key terms when talking about statistical significance. Let's use our Three Stooges research as an example. The first is confidence interval. If we find that 34% of our survey classified the Three Stooges as very funny, that's our sample statistic, we wouldn't want to say that exactly 34% of the U.S. population think the Three Stooges are very funny. We'd like a little bit of wiggle room so that we can say something like, we're fairly sure, had we been able to interview everyone in the U.S., between 30 and 38% would say the Three Stooges are very funny. We are estimating population parameters. Another way to say it is that we are fairly sure that the true value of the population parameter is within this confidence interval, in this case between plus or minus 4% of our sample statistic of 34%. The confidence interval then, sometimes abbreviated as CI, is the possible range of values for a variable in a population, calculated from a sample of that population. You can do this as means as well as percentages. But if you listen carefully to what I said, I used the words fairly sure. How sure I am relates to the second key term, confidence level. If you're like me, if someone asks you how sure you are of something, you'll want some wiggle room here too, to allow for the remote possibility that you might be wrong. So you might quantify your level of confidence by saying, I'm 95% sure. That 95% figure is your confidence level, which is the probability of a calculated value occurring. In research, the most commonly used confidence levels are associated with the standard deviations we mentioned earlier. That's why the trip down memory lane, as well as one not so explicitly associated, which is 90%. Using our Three Stooges example, where we found that 34% of our survey respondents said the Three Stooges were very funny, we could say that we are 95% confident, our confidence level, that had we asked the entire population instead of a sample, we would find that between 30 and 38% of them, our confidence interval, think the Three Stooges are very funny. This is often reported in research as between plus or minus 4% at the 95% confidence level. And again, you can use this for both percentages and means. Something to keep in mind, however, is the relationship between the confidence interval and the confidence level. The more confident you want to be, the larger the range or confidence interval you will have. In other words, if you want to improve or increase your confidence level from 95 to 99%, meaning you are allowing yourself less wiggle room for error, you will have to increase your wiggle room for the range or the confidence interval. Let's see how this works using our sample statistic of 34%, where previously we said that a 95% confidence level translates into a confidence interval ranging from between 30 to 38%, plus or minus 4% of our sample statistic. This means that we are willing to tolerate no more than a 5% error. Think about it. If we are 95% confident, that leaves room for 5% error. We are acknowledging that there is a 5% chance that we could be wrong. If, however, we want to be more confident, say 99% confident, we have to expand the range, maybe plus or minus 6%, meaning we are 99% sure that the actual percentages in the population would be between 28 and 40%. If, however, we are willing to reduce our confidence level to 68%, we would reduce our confidence interval as well. Most of the time, we aren't willing to live with this last confidence level of 68%. In fact, the most frequent confidence level used is 95%. But occasionally you may see a 90% confidence level with the same principles applied. One last thing to keep in mind is that we've been using the sample statistic of 34% because that's what our survey results of 400 people said. However, we usually establish the confidence level and confidence interval we're willing to live with before we conduct the research, Not knowing what our research finding will be, we identify what we're willing to live with. The worst case scenario, however, is that 50% of the people will give one answer and the remaining 50% will give an alternative answer. So when you read or hear about confidence intervals and confidence levels, they're usually based upon this 50-50 worst case scenario. Just a few final points about working with a sample rather than the full population. The distribution of the sample results is called the sampling distribution. If you graphically displayed your data, you could see how the data are distributed in your sample. You may hear the term standard error instead of standard deviation. While there is a distinction between the two, I'm not going to go into it here. Just know that some people use standard deviation to calculate confidence levels, and some use standard error of the mean. What is important to know about the standard error is that it is related to sample size. Standard error decreases as the number of observations in your sample increases. The larger your sample size, the more confident you can be that your sample is representative of your population. That's because as your sample size increases, your statistic is based upon more information and becomes more accurate, so its standard error decreases. Just a quick example. Assume we are interested in a 95% confidence level. Using the 50-50 scenario we talked about previously, if your survey sample size is 400, your confidence interval is plus or minus 4.9%, meaning we are 95% sure that the true value of the population parameter is between 45.1 and 54.9%. If you increase the sample size to 1200, however, using the same 95% confidence level, your confidence interval would be much smaller, between 47.2 and 52.8%, plus or minus 2.8%. Dropping the sample size to 100 yields a confidence interval within plus or minus 9.8% of that 50%, or a larger range between 40.2 and 59.8%. Processing time. What does statistical significance mean and what does it not mean? What is the difference between a statistic and a parameter? And what is the relationship between the confidence interval and the confidence level? After this discussion, I'm fairly sure that you have a better understanding of the concepts related to statistical significance. How sure? Well, I'll have to work on calculating that later.